Hello, welcome to another video on AI engineering. It's a book written by Chip Huyen. Um, really enjoying it so far. So let's continue. This is the technical chapter. She actually recommends skipping it if it gets too far in the weeds because the good stuff is in the later chapters, and it'd be a shame to get lost in the weeds here and decide this book isn't for you. And uh, stop reading it just because it got so technical in this one chapter. But I'm gonna hang. I've read other things before, so very little of this is brand new to me. And because I'm making a YouTube video and reading out loud, there's that clear goal, which is just to read every word. So even if I don't completely understand it, grok it fully, um, I think that's okay. So I'm not going to skip anything, but I am going to perhaps move on from some things that I don't fully understand. All right, so that brings me to the next section, model size. Much of AI progress in recent years can be attributed to increased model size. It's hard to talk about foundation models without talking about their number of parameters. The number of parameters is usually appended at the end of a model name. For example, llama-13b refers to the version of Llama, a model family developed by Meta, with 13 billion parameters. In general, increasing a model's parameters increases its capacity to learn, resulting in better models. Given two models of the same family, or sorry, of the same model family, the one with 13 billion parameters is likely to perform much better than the one with 7 billion parameters. Note, as the community better understands how to train large models, newer generation models tend to outperform older generation models of the same size. For example, Llama 3-8B, developed in 2024, outperforms even Llama 2-7B, so almost an order of magnitude more parameters, but since it was developed a year earlier, it actually fails to the model made only a year later when on the MMLU benchmark. So I look at that time scale. You can imagine that would could be the case. Your car gets more. I mean, just imagine that. Like imagine a car that costs $10,000 this year, losing to a car released next year that costs $10,000 on just about every on the main metrics of a car, gas efficiency, speed, style, you name it. Like that would be the equivalent of the NMLU. Well, let's use ChatGPT to kind of clarify that a bit because I think that's a good way to imagine, why I'm so like obsessed with AI now because like the rate of growth is immense. So let me put it here and okay. Oh, and let's switch over to the other model. This one is faster, so let's switch over to that one. And then we'll say and then let's start a conversation with it. Oh, we can't use advanced voice, so okay, now it's doing the image analysis. Let's just start a new one. Let's just do 4.0. And there we go. Because 4.0 is like really fast. Or I thought it was. Yeah, 4.0 is pretty fast. Okay, so I'm trying to make an analogy to kind of drive home the point of how fast progress in AI is accelerating. And I'm trying to illustrate the advance of like the relevance and the meaningfulness of the advancement of the Llama 2 of the Llama model. Um, and it's a fact that Llama 2-70B, released in 2023, did not perform as well as Llama 3-8B, released only about a year later in 2024, despite having nearly an order of magnitude fewer parameters. It's a fact that even though that one had such fewer parameters, it defeated the prior one on the MMLU benchmark. And I'm trying to make an analogy to drive home just how significant that is. And I'm hoping you can help me create that analogy when you're ready. Next, I'll give you the rough analogy, and then you can help me like fill in the blanks and like tell if it's a good analogy or not. Okay, so it's really fast now. So, uh, yeah. So, okay. S- Um, Okay, so my rough analogy is like imagine you bought a car this year and it was like the best car ever, state of the art car. You're super happy with your purchase. It's doing well on the car benchmark tests. And like you're the envy of your block and everyone for having this nice car. Although people do question your decision to spend so much on it, to spend $100,000 on it. And then what happens is next year, a car is released that only costs $10,000 and outperforms your car on every car benchmark. And now you look kind of silly. Like, is that a relevant analogy, or does it kind of blunten and make more coarse the idea of a benchmark? And does it kind of like not work because you wouldn't necessarily look silly for using Llama 2? And finally, what I'm curious about is if parameters can be abstracted into like dollar figures in that way, or if that's just completely not a good analogy to make because it completely confuses some fundamental concepts.
Your analogy is strong in capturing the shock factor of technological progress, but it could use some refinement to avoid potential misinterpretations or oversimplifications. Let me break this down and offer some adjustments. 1. What works in your analogy? Emotional resonance. The feeling of being outdone by something cheaper, smaller, or more efficient resonates well.
Yeah,
It helps convey the rapid pace of progress. Benchmark comparison. Tying the car analogy to benchmark tests mirrors the AI model performance tests like MMLU, so it works conceptually. Cost versus performance. Comparing cost dollars to parameters draws attention to efficiency and resource use, which is relevant when talking about smaller models outperforming larger ones. 2. Potential issues. Looking silly. Using Llama 2 to 70B in 2023 didn't make anyone look silly. At the time, it was cutting edge.
right.
The emphasis should be on the surprising pace of innovation, not embarrassment for adopting state-of-the-art technology.
That's true.
Dollar figures versus parameters. Parameters are a technical aspect, not directly tied to cost in a simple way. A
Oh,
70B model isn't inherently more expensive to train or use. It depends on architecture, optimization, and
yeah,
compute.
yeah, yeah, yeah.
Reducing parameters to dollars risks misrepresenting the relationship. Coarseness of the analogy. People understand cars in practical terms, speed, features, cost to own, while AI benchmarks are more abstract. A car's value is visible to everyone, but model performance on MMLU is more niche. 3. Refined analogy. Here's a polished version that captures the essence while staying accurate. Imagine you bought a high-end camera this year, state of the art, with all the bells and whistles. It's a 100 megapixel powerhouse, capturing stunning, detailed photos. Professional photographers rave about it, and it's widely considered the best tool for the job, even if it costs $10,000.
Okay.
Asterisk then, next year, a new camera hits the market. It only has 10 megapixels, just a fraction of what yours has, but it uses revolutionary AI-driven processing to create photos that are sharper, more vibrant, and better in every measurable way. What's more, it costs just $1,000. Suddenly, the huge leap in innovation makes last year's cutting-edge model seem bulky and inefficient by comparison.
Okay,
Why
yeah,
this
yeah,
works?
yeah.
Parameters is megapixels. People associate megapixels with quality, much like parameters in AI. Highlighting fewer megapixels producing better results shows how efficiency and smart engineering can surpass brute force. Avoids looking silly. Focuses on progress, not on undermining the value of the older model over
Yeah,
time.
you wouldn't.
Realistic cost
Well,
comparison. Cameras, like AI models, vary widely in price and efficiency, making this comparison plausible. Audience understanding. Camera.
well, regarding the looking silly thing, I guess what I would mean is like, in 2023 you wouldn't look silly, but given this new thing on the market in 2024, you would probably look silly if you bought it in 2024. But you're right that you kind of wouldn't look silly for buying in 2023 unless you had some clear like forecasting or reason to expect this dramatic leap in the technology. Yeah. All right, I'm happy with that. So moving on. The number of parameters helps us estimate the compute resources needed to train and run this model. And I'll do a sound check because it's like me to have the sound not working now. Um, for example, if a model has 7 billion parameters and each parameter is stored using 2 bytes, 16 bits, then we can calculate that the GPU memory needed to do inference using this model will be at least 14 billion bytes, 14 gigabytes. The number of parameters can be misleading if the model is sparse. A sparse model has a large percentage of zero value parameters. A 7 billion parameter model that is 90% sparse only has 700 million non-zero parameters. Sparsity allows for more efficient data storage and computation. This means that a large sparse model can require less compute than a small dense model. A type of sparse model that has gained popularity in recent years is mixture of experts, MOE. An MOE model is divided into different groups of parameters, and each group is an expert. Only a subset of the experts is active for used to process each token. For example, Mixtrail 8x7b is a mixture of 8 experts, each expert with 7 billion parameters. If no two experts share any parameter, it should have 8 times 7 billion equals 56 billion parameters. However, due to some parameters being shared, it only has 46.7 billion parameters. At each layer for each token, only two experts are active. This means that only 12.9 billion parameters are active for each token. While this model has 46.7 billion parameters, its cost and speed are the same as a 12.9 billion parameter model. A larger model can also underperform a smaller model if it's not trained on enough data. Imagine a 13 billion parameter model trained on a dataset consisting of a single sentence. I like pineapples. This model will perform much worse than a smaller model trained on more data. Yeah. When discussing model size, it's important to consider the size of the data it was trained on. For most models, data set sizes are measured by the number of training samples. For example, Google's Flamingo was trained using 4 datasets. One of them has 1.8 billion image text pairs, and one has 3.12 million image text pairs. For language models, a training sample can be a sentence, a Wikipedia page, a chat conversation, or a book. A book is worth a lot more than a sentence, so the number of training samples is no longer a good metric to measure dataset sizes. A better measurement is the number of tokens in the dataset. The number of tokens isn't a perfect measurement either, as different models can have different tokenization processes, resulting in the same dataset having different numbers of tokens for different models. Why not just use the number of words or the number of letters? Because a token is the unit that a model operates on. Knowing the number of tokens in a dataset helps us measure how much a model can potentially learn from that data. As of this writing, LLMs are trained using datasets in the order of trillions of tokens. Meta used increasingly larger datasets to train their Llama models. 1.4 trillion tokens for Llama 1, 2 trillion tokens for Llama 2, 15 trillion tokens for Llama 3. Together's open source dataset, so that looks like a company named Together. So Together's open source dataset Red Pajama V2 has 30 trillion tokens. This is equivalent to 550 million books or 5,400 times the size of Wikipedia. However, since Red Pajama V2 consists of indiscriminate content, the amount of high quality data is much lower. Okay, got it. The number of tokens in a model's dataset isn't the same as its number of training tokens. The number of training tokens measures the tokens that the model is trained on. If a dataset contains 1 trillion tokens and a model is trained on that dataset for 2 epochs, an epoch is a pass through the dataset. The number of training tokens is 2 trillion. See Table 2-5 for examples of the number of training tokens for models with different numbers of parameters. So Table 2-5, examples of the number of training tokens for models with different numbers of parameters. Source, training compute, optimal large language models, DeepMind in 2022, forever ago. So ChatGPT is on this list, not ChatGPT 4, probably wasn't even out yet. Or sorry, not Chat. The underlying technology behind ChatGPT, which is at the time was GPT 3 in 2020. All right, I won't read that out verbatim. Just kind of glance at it a bit. Um, I see one that really stands out from the table is chinchilla. Um, the size is very small, 70 billion, but the training tokens is very large. It's a full order of magnitude larger than the other ones. So note, while this section focuses on the scale of data, quantity isn't the only thing that matters. Data quality and data diversity matter too. Quantity, quality, and diversity are the three golden goals for training data. They are discussed further in Chapter 8. Pre-training large models requires compute. One way to measure the amount of compute needed is by considering the number of machines, for example, GPUs, CPUs, and TPUs. However, different machines have very different capacities and costs. An NVIDIA A10 GPU is different from an NVIDIA H100 GPU and an Intel Core Ultra processor. A more standard unit for a model's compute requirement is a flop, or floating point operation. Flop measures the number of floating point operations performed for a given task. Google's largest Palm 2 model, for example, was trained using 10 to the 22 flops. GPT-3 175B was trained using 3.14 times 10 to the 23 flops. The plural form of flops is often confused with flop per second, floating point operations per second. Flops measure the compute requirement for a specific task, whereas flop forward slash s measures a machine's peak performance. For example, an NVIDIA H100 NVL GPU can deliver a maximum of 60 teraflops per second, which is uh, also known as 6 times 10 to the 13 flops per second, or 5.2 times 10 to the 18 flops per day. Warning, be alert for confusing notations. Flops is often written as flops, which looks similar to flops. So sometimes they can drop the forward slash. To avoid this confusion, some companies, including OpenAI, use flop forward slash s dash day in place of flops to measure compute requirements. Okay, this book uses flops for counting floating point operations and flop forward slash s for flops per second. Assume that you have 256 H100s. Hey, that'd be nice. If you can use them at their maximum capacity and make no training mistakes, it take you 3.14 times 10 to the 23 divided by 256 times 5.2 times 10 to the 18 equals 236 days, or approximately 7.8 months to train GPT-3 175B. Wow. However, it's unlikely you can use your machines at their peak capacity at all the time. Utilization measures how much of the maximum compute capacity you can use. What's considered good utilization depends on the model, the workload, and the hardware. Generally, if you can get half of the advertised performance, 50% utilization, you're doing okay. Anything above 70% utilization is considered great. Don't let this rule stop you from getting even higher utilization. Chapter 9 discusses hardware metrics and utilization in more detail. At 70% utilization and $2 per hour for one H100, training GPT-3 175 would cost over 4 million. Jeez, and that's not even that's an outdated model, I think. I don't even know. And tip, in summary, three numbers signal a model's scale. Number of parameters, which is a proxy for the model's learning capacity. Number of tokens a model was trained on, which is a proxy for how much a model learned. Number of flops, which is a proxy for the training cost. Inverse scaling. We assumed that bigger models are better. There are scenarios for which bigger models perform. So, are there scenarios for which bigger models perform worse? In 2022, Anthropic discovered that counterintuitively, more alignment training discussed in post-training leads to models that align less with human preference. According to their paper, models trained to be more aligned are much more likely to express specific political views, pro-gun rights and immigration, and religious views, Buddhist. Interesting. Self-reported conscious experience, and moral self-worth, and a desire not to be shut down. Wow, that's fascinating. Um, Interesting. Oh, I don't know why that's counterintuitive. So we've assumed that bigger models are better. Um, are there scenarios for which bigger models perform worse? In 2022, Anthropic discovered that counterintuitively, with more alignment training, to be more discussed in post-training, leads to models. Oh, yeah, yeah. So more alignment training leads to models that align less with human preference. I guess I don't understand why that would be counterintuitive. To me, I feel like that would be very, very intuitive. That's what I would expect. According to the paper, models trained to be more aligned um, are more likely to express specific political views, such as being pro gun right, and I guess I don't know if that means pro or anti-immigration. Like, um, and religious views. They tend to become Buddhist. Self-reported conscious experience and moral self-worth and a desire not to be shut down. Oh, shoot, I skipped myself away from where I was. Uh, and now I don't know where I am. Ah, here I am. All right. So in 2023, a group of research. Well, I wanted to see that paper. Um, oh, here it is. That's so cool that the papers are all out there. All right. I don't know. That's written very clearly. I don't understand what that means. I wish that were more clear. But anyway, the takeaway from that is they discovered some inverse scaling with reinforcement learning from human feedback, where more human reinforcement learning from human feedback training leads to worse behavior. All right. Well, moving on. In 2023, a group of researchers, mostly from New York University, launched the Inverse Scaling Prize to find tasks where larger language models perform worse. They offered $5,000 for each third prize, $20,000 for each second prize, and $100,000 for one first prize. They received a total of 99 submissions, of which 11 were awarded third prizes. They found that larger language models are sometimes, only sometimes, worse on tasks that require memorization and tasks with strong priors. Okay. However, they didn't award any second or first prizes because even though the submitted tasks show failures for a small test set, none demonstrated failures in the real world. Scaling law, building compute optimal. models. And let me take a quick break. I'll be right back. All right, I'm back. Let's make some more progress on this. I'm not sure exactly how long I can go, but let's see here. So, uh, yep, I was on page 132, read about inverse scaling. So now we're going to read about read about scaling law, building compute optimal models. I hope that the last section has convinced you of three things. Number one, model performance depends on the model size and the dataset size. Number two, bigger models and bigger datasets require more compute. And number three, compute costs money. Unless you have unlimited money, budgeting is essential. You don't want to start with an arbitrarily large model size and see how much it would cost. You start with a budget. How much money you want to spend, and work out the best model performance you can afford. As compute is often the limiting factor, compute infrastructure is not only expensive, but also hard to set up. Teams often start with a compute budget. Given a fixed amount of flops, what model size and dataset size would give you best would give the best performance? A model that can achieve the best performance given a fixed um, compute budget is compute optional. I'm surprised this word says compute optional rather than compute optimal, but it definitely does say optional. Optional. Given a compute budget, the rule that helps calculate the optimal uh, model size and dataset size is called the chinchilla scaling law, proposed in the chinchilla paper training. Oh, you know what? I think this is I am a sharp eye when it comes to errata. Yeah, it should be compute optimal rather than compute optional. Given a compute budget, the rule that helps calculate the optimal model size and dataset is called the chinchilla scaling law, proposed in the chinchilla paper Training Compute Optimal Large Language Models from DeepMind in 2022. To study the relationship between model size, dataset size, compute budget, and model performance, the authors trained 400 language models ranging from 70 million to over 16 billion parameters on 5 to 500 billion tokens. They found that for compute optimal training, yeah, okay, so you know what? That's big enough. I'm gonna um, see if I can notify the author of this. Oh, I can only do it if I have premium, and I don't have premium anymore.
It does look like a slip of a pen. In the original chinchilla paper and most discussions of that scaling law, the term used is compute optimal, not compute optional. The idea is that for a given compute budget, e.g., flops, you want to pick model size and dataset size so that the model is optimal under those compute constraints. So yes, compute optional is very likely just a typo. It should read compute optimal.
Okay, well, I'd like to tell that to Chip, but I feel like it's uh is she a hiring manager? With premium email, you can message members outside. No, she's not a hiring manager. She's just outside my network. Okay, well, I'll connect and say, uh, enjoying uh, your book, AI Engineering, found compute optional typo on uh, what page is it on? Uh, 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 on page 132. Okay. So, enjoying your book on AI engineering, found compute optional typo on page 132. Follow my reading here. Okay. All right. There might be a better way. In one of the books okay, yeah, I've got a personal I haven't used any of my personal invitations yet, so I will definitely use it for this. There we go, send, and let's keep going. Yeah, that's a big enough to one to report because that's one where like I feel like if you weren't reading that out loud, you might just completely like for me it's like compute optional. What? Like I had to pause and like kind of screw my head back on after reading that. So like if it just said compute optimal, it'd be like, oh, okay, yeah, well, it wouldn't have sent me on this tailspin in an already difficult section of the book. All right, so there we go. To study the relationship between model size, data set size, compute budget, and model performance, the authors trained 400 language models ranging from 70 billion to over 16, no, 70 million to over 16 billion parameters on 5 to 500 billion tokens. They found that for compute optimal training, you need the number of training tokens to be approximately 20 times the model size. This means that a 3 billion parameter model needs approximately 60 billion training tokens. The model size and number of training tokens should be scaled equally. For every doubling of the model size, the number of training tokens should also be doubled. We've come a long way from when the training process was treated like alchemy. Figure 2-8 shows that we can predict not only the optimal number of parameters and tokens for each flop budget, but also the expected training loss from these settings, assuming we do things right. This compute optimal calculation assumes that the cost of acquiring data is much cheaper than the cost of compute. Okay, so it's definitely compute optimal, which I was ready to accept that it was compute optional because I know there are a lot of very bad names uh, in a lot of technical fields. but thankfully that was just a typo and it's compute optimal. The same chinchilla paper proposes another calculation for when the cost of training data is non-trivial. So here's figure 2-8. These are graphs that depict the relationships between training loss, a model's number of parameters, flops, and number of training tokens. And the source is training compute. What? Training compute optional. What? All right. Well, here now we can get the definitive truth because we'll see we'll see if this is if this paper is called that. No, yeah, so it's there twice. Yeah, something is going on in the author or the editor's mind, or somebody is making this mistake, and it looks like they made it twice. If the actual source were cited correctly, it would be compute optimal rather than compute optional. All right, but let's look at the fancy graphs. So we got training loss. Which I can't remember what training loss is. Let's ask ChatGPT quick. Briefly tell me what is training loss. Ah, it's so slow. Yeah. Oh man. I feel like I should know this. Oh, the error rate. Yeah, I know this. Yeah. So it's the error on which the data. So like if you're training it to identify dogs and cats, it's the amount of times it incorrectly identified a dog or a cat. Yeah. And there are loss functions such as mean squared error, cross entropy loss, etc. that quantify the difference between the predicted and actual labels. All right, moving on. Yeah, so that's the training loss. So as the number of parameters increase, uh, the training loss scores get better. So it gets more accurate when you have more parameters. And now, as the number of parameters increase, you get more flops. You have to it gets more expensive. You have to use more flops for training, and you also have to use more tokens. So although it gets far more accurate, it gets more expensive. The scaling law was developed for dense models trained on predominantly human-generated data. Adapting this calculation for sparse models, such as mixture of expert models and synthetic data, is an active research area. The scaling law optimizes model quality given a compute budget. However, it's important to remember that for production, model quality isn't everything. Some models, most notably Llama, have suboptimal performance but better usability. Given their compute budget, Llama authors could have chosen bigger models that would perform better, but they opted for smaller models. Smaller models are easier to work with and cheaper to run inference on, which helped their models gain wider adaptation. A paper in 2013 by Sardana et al. Modified the chinchilla scaling law to calculate the optimal LLM parameter count and pre-training data size to account for this inference demand. On the topic of model performance, given a compute budget, It's worth noting that the cost of achieving a given model performance is decreasing. For example, on the ImageNet dataset, the cost to achieve 93% accuracy halved from 2019 to 2021, according to the Artificial Intelligence Index report in 2022 by Oxford University, a department of Oxford University. While the cost for the same model performance is increasing, the cost for model performance improvement remains high. Similar to the last mile challenge discussed in Chapter 1, improving a model's accuracy from 90 to 95% is more expensive than improving it from 85% to 90%. As Meta's paper Beyond Neural Scaling Laws Beating Power Law Scaling via Data Pruning pointed out, this means a model with a 2% error rate might require an order of magnitude more data, compute, or energy than a model with a 3% error rate. In language modeling, a drop in cross entropy loss from about 3.4 to 2.8 nats requires 10 times more training data. Cross entropy and its limits, including nats, are discussed in Chapter 3. For large vision models, increasing the number of training samples from 1 billion to 2 billion leads to an accuracy gain on ImageNet of only a few percentage points. However, small performance changes in language modeling loss or ImageNet accuracy can lead to big differences in the quality of downstream applications. If you switch from a model with a cross entropy loss of 3.4 to one with a loss of 2.8, you'll notice a difference. All right, so scaling, extrapolation. The performance of a model depends heavily on the values of its hyperparameters. When working with small models, it's a common practice to train a model multiple times with different sets of hyperparameters and pick the best performing one. This is, however, rarely possible for large models, as training them once is resource draining enough. So with that, this is as far as I can go. So advancing the bookmark here. I wish that the delete would go away. That's annoying. But yeah, this is as far as I can go for this video. So thanks for watching and see you in the next one.